All right, continuing where we left off. Um, we were talking about polarity and like dissolves like, and we are talking in the last video about how nonpolar solutes will require nonpolar solvents. So iodine can only dissolve in a nonpolar solvent, or oil which is nonpolar will not dissolve in water which is polar. It needs a nonpolar solvent to dissolve. Okay, so in this study check, it says identify the solute in each of the following solutions. So remember, as I mentioned, the larger quantity is the solvent. So the lesser quantity would be the solute, all right? So here, 2 grams of sugar, that's the solute. Now, in 60 mils of ethyl alcohol, 30 mils of methyl alcohol, the lesser quantity is the 30 mils, so therefore methyl alcohol is the solute. 55 mils of water and 1.5 grams of NaCl. The lesser quantity is 1.5 grams of NaCl, so that's the solute. 200 mils of oxygen, 800 mils of nitrogen. The lesser quantity is 200 mils oxygen, so that's the solute. When solid lithium chloride is added to water, it dissolves because the positive lithium ions are going to be attracted to the negative oxygen atoms, all right? Positive, negative are always going to be attracted to each other. The negative chloride ions are going to be attracted to the positive hydrogen atoms of water. Which of the following solutes will dissolve in water? So remember, it has to be polar, or it has to have charge, like either ionic or a polar compound. So sodium sulfate would dissolve in water. HCl, hydrogen chloride, is polar, so it would also dissolve in water. Iodine is nonpolar. Gasoline, like oil, is nonpolar, so it would not dissolve in water. So this is section 9.2. So we're going to be talking here about electrolytes. And you know instinctively by experience that when you get dehydrated, the recommendation is that you hydrate yourself, especially take things that have added electrolytes in them to overcome the dehydration. So here you see a nurse preparing an electrolyte solution, and this is to ensure that the cells are well hydrated and they are in proper functioning order. All right. So electrolytes are usually associated with a lot of the ions like sodium, potassium, and so on. And all of these are involved in maintaining the body functions, the cell functions. So an electrolyte, the definition of electrolyte, all right, is that it's going to create electrons in solution, all right? So the movement of electrons, that's basically electricity, all right? And how does that happen? For example, when sodium chloride dissolves in water, you're getting sodium ions and chloride ions, all right? So these ions are floating around. It completely breaks up. You can ignore this left side because once that sodium chloride gets into water, there's no longer any solid left. It's completely broken up into ions, all right? All you see is the sodium ions and the chloride ions. That's all there is in solution. Now, if you have electrodes inserted into the sodium chloride solution, like you see here in the picture, with a positive electrode with a negative electrode and a positive electrode, you will see that the chloride ions will migrate towards the positive electrode. The sodium ions will migrate towards the negative electrode. And if those electrodes are connected to a light bulb, because of the circulation of electrons, the circuit is complete and the light bulb lights up. All right. Now it's got a very strong signal showing that this solution, excuse me, is a strong electrolyte solution. All right. So going back to where we were, again, sorry for that interruption. So it shows that this is a strong electrolyte solution because it's producing positive and negative ions. It's broken up into water 100%. All right. There's only ions in water once it's dissolved into water. All right. And because it's producing such a strong electric current, because of the migration of those ions and electrons, and therefore the light bulb gives you a strong signal. A weak electrolyte, on the other hand, and you can see this double arrow, which is also an indicator of a weak electrolyte. So hydrogen fluoride does dissolve in water. However, unlike sodium chloride, it breaks up, but only partially. All right, so a little bit of ions are formed, maybe 0.3% or so of it breaks up. So a few ions are formed, but if you look at most of the hydrogen fluoride, it's unbroken. It's remaining as intact molecules. All right, so you do get the signal, which is much weaker. All right, so the signal strength is weaker. All right, the light bulb does light up, but it's weak. And most of the hydrogen fluoride is existing as unbroken molecules. All right, so in a weak electrolyte, you see some ions, but mostly molecules. In a non-electrolyte like methanol, it's dissolving in water because of hydrogen bonding. However, no ions are being produced, all right? Or sucrose or glucose, they would dissolve, which is why you see AQ, which means that once they dissolve into water, you no longer see a solid. They're all aqueous, dissolved into water because of hydrogen bonding. However, no ions are produced, and therefore you don't see any kind of reaction with the light bulb. So to summarize, types of electrolytes: strong, it breaks up completely, 100% dissociation. All right, so all you see in solution is ions, and it does conduct electricity. All right, strong light bulb signal. And a lot of ionic compounds are strong electrolytes. Not all, but most of them are. All right, and then a lot of acids and bases are as well are strong electrolytes. Weak electrolytes, they break up a little bit, not much. So mostly they're molecules, but there are some ions, a little bit of ions. All right, and then you will see that in the representative reaction, there's a double arrow showing that it kind of goes both ways. All right, and so there are those these are polar compounds. Especially HF is a polar compound, water is a polar compound, ammonia is a polar compound, and acetic acid is also a polar compound. And so you see that they do dissolve in water. They kind of partially break up, but they don't really form too many ions. Non-electrolytes dissolve in water. However, it only produces those aqueous molecules, intact molecules. So a lot of these are sugars and methanol, alcohols, small alcohols. So they dissolve in water because of hydrogen bonding. However, they don't produce ions. So complete each for strong electrolytes in water. All right. So if it is strong, it has to be broken up 100%. All right, so the calcium has to separate from the chloride ions. All right, so it has to be C. This doesn't exist. Once it's broken up, each chloride has got a negative charge, so there's two of those. All right, so the correct answer would be C. Similarly here, it'll have to be completely broken up into metal and non-metal part. This is a polyatomic ion, phosphate. All right, so there are three of these potassiums and one of the phosphate. All right, okay, so the only answer is A. Which of the following reactions represent the dissociation of a strong electrolyte in water? So remember, complete breakup, 100%. All right, so this can't be it, this can't be it, but this is a good choice because you have the sodium separating out from the sulfate. Okay. The dissociation, write the equation for the formation of a solution from each of the following. The dissociation of potassium potassium chromate. All right. So here you have two potassiums and one of the CrO4, the chromate ion. All right. So that would be 2K plus AQ and CrO4 2 minus AQ. Partial dissociation of H3PO4. So one of the H's might come off, and then what's left is the H2PO4 negative, and then C12H22O11, which is sucrose, and so that would dissolve, but instead of the S, you would have AQ on the other side, and it would look something like this. All right, next we come to defining equivalence. All right, so what does this word mean? EQ, equivalent. All right, equivalent is, as it says here, if you have 1 mole of an ion, the charge carried by that 1 mole of ion, all right, that's is the definition of EQ or equivalent, right? So the charge provided, the amount of electrolyte or charge that is provided by 1 mole of an ion, all right, in solution, that is defined as EQ. So for example, 1 mole of sodium ion would provide a 1 EQ equivalent of charge. 1 mole of magnesium would be 2 EQ because magnesium ions have a 2 positive charge, all right? Or 1 mole of chloride would be 1 EQ. So you're just kind of looking at the magnitude of the charge, right? And most solutions, especially the IV solutions which are prepared in terms of milli EQ, which is 1,000th of an EQ. So, suppose you have 25 MEQ, milli EQ of Na sodium positive ions and 4 MEQ of the potassium positive ions. That means a total of 29 MEQ of the positive ions. So always in a solution, when preparing an IV solution, the positives have to be matched up with the negatives. So chloride ion, which is the only anion present in this particular IV solution, must be 29 MEQ. So the amount of negative charges must balance the amount of positive charges. Okay. And then again, we talked about definitions of EQ. If you look here, any of the 1 positive charges, they carry the number of EQs per mole of those ions of 1. If it is 2 positive, it's 2 EQ. If 3 positive, 3 EQ. Now, the other thing that you will notice is that phosphate has a 3 EQ. Iron 3 plus also has a 3 EQ. So there's no kind of charge to it. It is just the magnitude of the charge, and we'll stop here.